Now coming to the using Castiglione's theorem, finding deflection of beams. Here we know strain energy is equal to sigma 0 to L m square dx by 2 EI. This we have derived. Now first problem we'll take the cantilever beam with point load P. Question is find deflection at the free end using Castigliano's theorem. Now your strain energy is equal to sigma m square dx by 2 EI. Now we have to calculate m and substitute in this. So what is m? We have to consider cross section xx at a distance x from B. So m x at xx is equal to p into x. Substituting m in strain energy expression, so you have u is equal to 0 to L m is p fixed px whole square dx by 2 EI. Now 0 to L p square x square dx by 2 EI. To do integration, p square x cube by 2 into 3 will be 6 EI 0 to L. This is u. In substitute L, it becomes p square L cube by 6 EI. This is u. So what is Castigliano's theorem? Castigliano's theorem say, as per Castigliano's theorem, delta is equal to dou u by dou p. That implies differentiation above become p square will become 2p. 2p L cube by 6 EI. This will become delta is equal to p L cube by 3 EI. Deflection at the free end. Coming to the next problem. Cantilever with UDL. find deflection at free end. W kilonewton per meter. Now we have to find deflection at B, but we don't have any point load here. Therefore, to solve above problem by Castigliano's theorem, we need to assume a imaginary load Q at free end. So this cantilever, this is W kilonewton per meter. Here we are assuming point load Q. This is L. Again, to solve problem, U is equal to 0 to L m square dx by 2EI. We will assume one cross section x at a distance x from B. So m is equal to qx plus w x square by 2. Substitute this in shear energy. U is equal to 0 to L qx plus wx square by 2 whole square dx by 2EI. Now, as per Castigliano's theorem, displacement is equal to, here what we will do, first we will do the partial differentiation, then we will do the integration. Delta is equal to dou U by, see, we need displacement at this point. So what is the force here? Force is Q. So we have to do partial differentiation dou U by dou Q. Delta is equal to dou U by dou Q. 0 to L. Now this whole assuming as x square, so when we do partial differentiation, it will become 2x, 2 into whole thing, qx plus wx square by 2, and we are doing partial differentiation with respect to q, so whatever the term which is with association with q, that we have to write here, x dx by 2EI. 1 by EI is taking out 0 to L. Now multiply the x here, qx square plus w x cube by 2 dx. Now we will do integration. 1 by EI q x cube by 3 plus w x to the power of 4 by 4 to the 8, 0 to L. 1 by EI q x cube xl. cube by 3 plus w in the place of x l to the power 4 by 8. Now substituting q is equal to 0 because this is imaginary force, it will become w l to the power of 4 by 8 ei delta is equal to, this is how we calculate displacement at free end. The next problem is simply supported beam, load W, this is A, this is B. Find deflection under the load W. What will be the deflection at this point using Castigliano's theorem? Here simply supported we will find reactions. So RB into L is equal to WA, RB is equal to WA by L, and RA is equal to WB by L. So here we are having two parts, left part and right part. Here the limit is 0 to A and here the limit is 0 to B. So what we do is here, for example, for the first part, if I take cross section, mx1 is equal to RA into x. What is RA? WB x by L. This is mx1. For limit 0 to A, and for other part we will take one more cross section y to distance x. So here limit is 0 to B, from here to this one. mx2 is equal to RB into x. What is RB? WAX by L. Now u is equal to integration m square dx by 2ei. So we have to do here in by parts. That is, first limit it is 0 to A, m1 square dx by 2ei plus 0 to B, m2 square dx by 2ei. Substituting m1 0 to A, what is m1 square is w square b square x square by 2ei dx plus 0 to B, m2 square is equal to w square a square x square by L square 2ei I, here also L square. So when you do integration, W square B square x cube by 6 EI L square 0 to A plus W square A square x cube by 6 EI L square 0 to B. So in place of x you have to substitute A. W square B square A cube by 6L square EI plus W square A square B cube by 6L square EI. So now when you take common, W square A square B square by 6L square EI, A square, this will become A plus B, which is L. W square will have the value W square A square B square by 6L EI. This is delta. Displacement under load. W square A square B square by 6L EI. Suppose if the load, now what we got is for this case, this is A, this is B. Delta we got as W square this is U, W square A square B square by 6L EI. Now this is total strain energy. Now deflection is dou U by dou W. So it will become 2W A square B square by 6L EI. It will become W A square B square by 3L EI. This is actually delta. Now if the load is at mid span, then A is equal to B is equal to L by 2. Substituting in above equation, delta is equal to W L square to L square by 3 into L into 2 square into 2 square EI. From W L cube by this will become 2 square 2 square, 4 into 4 16 into 3 48, 48 EI. Delta is equal to WL cube by 48 EI when load is at mid span. So we got, this is the problem. When the load is eccentrically acting, then we got the delta as WS square B square by 3L EI. And when we substitute, when the load, for the same problem, if the load is acting at the center, we are substituting A is equal to L by 2 and B is equal to L by 2 in the above equation. We got W is delta is equal to WL cube by 48 EI. This is what we got previously in the previous methods. Okay. Next problem is, we have simply supported beam with UDL. Yes. This simply supported beam with UDL, W kilonewton per meter. Find displacement at center mid span of the beam. See here, this is the center. Same thing what we have done for cantilever. When there is no point load, what we have to do is, we have to assume a point load Q. Then we have to proceed the same thing, reactions RB into L will become W into L into L by 2 into Q L by 2. Then RB is WL by 2 plus Q by 2. Okay, in the same way RA will become WL by 2 plus Q by 2 because it's symmetric load. Now considering a cross section XX at a X from A, we need to find expression for moment at X. Mx is equal to Ra into X. See, this Ra, this is Ra, this is R, Ra into X minus this one, Wx square by 2, minus Wx square by 2. So M is equal to W, when we are substituting Ra, WLx by 2 plus Qx by 2 minus Wx square by 2. This is the expression for moment. Now we have to substitute this moment in strain energy equation. In place of M, we have to substitute. So now here what is happening is, it is symmetric. Left side and right side we are having same forces. So we can assume that from 0 to L by 2, 2 times. Twice 0 to L by 2. So this is M square dx by 2 EI. Now again what we have to do here is, first we will do partial differentiation because we want displacement at C. So we do dou U by dou Q. So this is for the simplification of the problem, because if you do integration then differentiation, it will become very big problem. So first we will do differentiation. So see here, twice 2EI is coming out, and now this whole thing will be acting as x square. So x square differentiation will become 2x, and We are doing differentiation with respect to q. So whatever the variable which is associated with q, that we have to write here, x by 2 dx. So then after simplifying, 1 by ei will be remaining, and this 2 and this 2 will be getting cancelled. So this is the wl, and this x we are multiplying again with this one. X will become x square, q x square by 2, w x square is x cube by 2. So this is what we are getting. Now we have to do integration for this. So dou u by dou q, this is what is the displacement, 1 by e 0 to L by 2. For this expression we have to do integration. So x square will become x cube by 3, 3 into 2 is 6, and x square will be again x cube by 3, 3 into 2 will become 6, and x cube will become x square by 4, x to the power of 4 by 4, 4 into 2 will become 8, 0 to L by 2. Now in place of x we have to put limit L by 2. So see, L is remaining same. In place of x, L cube by 2 cube, again L cube by 2 cube, and L cube by L to the power of 4 by 2 to the power of 4. So now we know q is equal to 0 because imaginary force. So after doing simplification, we will be remaining with 5 WL to the power of 4 by 384 EI displacement at midspan. This is how we are going to do for the beams. Now, if in the exam, if you are getting the problem, you have to do in the same procedure. If the question is do using the Cauchy-Coulomb theorem, the procedure what we have followed, we have to use the same procedure.